And now let me share the screen. Okay. Okay, guys, so today we're going to start, we're going to continue with our class. So just let me quickly go to the final part of the utility maximization problem with infinite dimensional problem, right? And so I want to take any questions. So I think Brice asked a question in the forum asking what was the difference between the first time we proved the utility representation theorem and the second time. So in the summer, we proved it for a finite choice set. So that means we have only finite many alternatives, right? But in some situations like consumption bundles, you can have infinite consumption spaces. Why is infinite? Because it can be any vector, any quantity, right? So that's infinite. So now, given that, we need a different proof, and I did such proof in the previous class. So the proof involved two steps. The first one was doing the representation theorem for a subset of the infinite space. In this case, is the a dense subset inside this space, which is the rational numbers, the product space of that, of the number of goods, QL. And then the key idea there is that even if we have infinite elements, is countably infinite, right? So we can actually put the elements one-to-one with the integers. So I created a utility representation there. And I use, again, the lower contour set, but instead of using cardinality, I use a probability measure algorithm, right? So this thing here is actually a probability measure that is any convergence sequence, right? And this was normalized between 0 and 1. So basically, like, if you remember your probability classes, what I'm doing is taking the measure of these lower contour set, right? So the idea is that, you know, the items that are higher up in the rankings, so the best, the most preferred items, have a larger lower contour set. So they're going to have a larger measure of it, right? For any positive measure. And I chose a particular one, is one of the index I. And this is not a uniform one, right? It has to be convergent. Remember that in this concept of the infinity spaces, there is no uniform distribution, right? So we need something convergent. And that's the proof, right? And then that's fine for the concept of the infinity case, but then we have to actually complete it and fill for the case of the infinite dimensional space, which is R. And we use the idea of density on reals. So the consequences of vectors that are rational entries and then converge to rational entries. And doing that, we work with the functions. Okay, so that's very good. But right now, one thing I want you to know, right, is that in this, to go to the infinity, we actually require to have continuity. Continuity made.
Sorry, Victor?
Yeah.
We're not hearing you clearly. Your voice.
Okay, so let me change the microphone. So, can you hear me now?
Yes, it's much better now.
Okay. Yeah, I have several microphones, so for some reason the one in the computer now is not working as great, but I changed to the one in my webcam. So sorry about that. Okay, so now we're going to study the utility maximization problem. Okay. Again, this part I'm going to go a little bit faster, and I'm going to focus on certain parts because we already covered it in the summer, right? So I'm not going to stop as much. So just, I'm going to remind you some things that we're going to use today. So paying the price of continuity, which I told you is not really a big price to pay because it's just a very technical assumption that is not testable, okay? So doing that assumption, we can now represent any rational order on this Euclidean space of quantities, of bundles, as a utility function. So that's pretty cool because now we can start using calculus, right? And other tools. So the fact that now we have a utility function, is back to the math most of us are more familiar with, okay? Right? So In particular, right, the people that haven't attended to the summer session, the recordings are basically available in OWL. I'm gonna post it through the Slack as well, so you can go to chapter 2. But yeah, I'm gonna remind you the main points today, so the class is contained. So the problem that we're gonna study now is instead of studying the maximization of a preference function, we're gonna study the maximization of a utility function. So we know now that we can do it, and that's a cool thing. So in particular, we want to, now the consumer, right, the brain we're modeling is maximizing a utility function that is representing a preference function. And the fact that it has a utility function, we know is even only if we've been rational, right? You have to be complete and transitive. So subject to what? To a budget constraint. In particular, this budget here for the chapter in Mascolel is going to be a linear budget. In particular, you know, this problem can be any budget, even nonlinear. As long as it's a compact budget, this next proposition is going to hold. I'm just going to go to the level of generality Mascolel uses, but you know, this is a very standard mathematical result. Maximizing a continuous function on a compact set has a solution, right? So very simple, a result from real analysis, and then we are going to get the existence as a corollary for our case. So in particular, we get that these conditions here, we have a budget, positive prices, and so on. It's not really completely necessary. But in fact, I'm just going to follow the notes in Mascolel. We have that the UMP has a solution. So the proof, we did it in the summer a bit. You're going to do it in the math class as well. So here I'm not going to go over it. The key idea is that this problem is always producing a solution. So that means the choice correspondence generated by maximizing a utility function is always not empty. So remember, we had this little discussion in previous classes about empty correspondences, right? What does it mean? We may have undecisive consumers and decisive households. Like for instance, you may have these households doing this majority voting in pairwise comparisons using their own strict preferences, and then you may have this Condorcet paradox, right? And these households may be, for instance, undecisive, so you cannot reach a decision. So now, the moment you have a utility function, so you eliminated any lack of transitivity and any lack of completeness, now you're going to produce, and of course with continuity, you're going to produce always a maximum. So that means that choice correspondences will never be empty here. So rational consumers will always make a decision. Okay? So that's just a corollary of our assumptions.
The solution is not, Victor, the solution is not unique, right? It can have more than one solution, the utility maximum.
So at this stage, we say there is at least one solution. It can be, of course, a set solution. It can be a singleton solution. Now, the next step is going to tell you more about the solution. So what we call the Marshallian demand correspondences is the set of solutions of this maximization problem, okay? So this is the one that maximizes utility subject to the budget constraint. And of course, we know it's not empty. There exists a solution. More important is compact value. So it means that the solution for any P and W that characterize a choice set is a compact set. So that means it's closed and bounded, right? So you don't have, you're never demanding infinite amounts of anything, right? So you always get something nice and bounded. And also you have upper ME continuity. Again, I told you to check the wiki and the math part on that. This notion of ME continuity is, of course, a weakening of continuity. We defined it as well in the previous class. But in general, you get some sort of continuity, right? And in particular, we also have that the value function, which is the utility function evaluated at any element in the set of solutions, is actually continuous, okay? So all of this is very convenient for mathematical purposes. It's not really anything behavioral. So all of these consequences are not really testable, right? So all of them are technical properties that are nice to have, but they are not testable nor important behaviorally. Do you understand? So for instance, you can never test that a set is compact, right? Because you have to, especially in infinite sets, you have to check closedness, which is defined sequentially, right? So you can never do that. And you can also, you cannot check continuities, I mentioned. So all of these things are technical properties of my problem that are very nice to have. And we're going to use them in our technical proofs. but they are not anything behavioral. So what I want you to understand is that this first set of results are technical results. And later on, as we finish the chapter, we're going to end up with the implications of utility maximization. Again, revisiting the GARP, the work, and also implications in terms of the differential behavior, so elasticities behavior, okay? So these are going to be testable implications that are meaningful, but these right now are just technical implications. Also important for proofs, but not really behavioral important. Again, this follows from this famous Berg's theorem. And again, we gave more details in the summer, but this proof is trivially following for application of this Berg's theorem, okay? So I'm not gonna do it. So right now, we're gonna remember we had this condition on our rationality model. So on top of having a utility function that is continuous, we also want it to be locally non-satiated. So we say something is locally non-satiated and reminding you if you have any bundle X, and then for any epsilon, any potentially small positive value, there exists another Y bundle such that the distance, according to some distance in this Euclidean space, thing of the Euclidean distance, is less than or equal than epsilon. This implies that Y is strictly greater than X. So for any X, there is always something better around. So I already explained this in the summer. This means that I'm ruling out thick indifference curves. So in fact, they have to be curves. They cannot be, they have to be low dimensional. So if I take anything around a point, I'm going to find better things than that object. So there is no large manifolds of indifference, right? They have to be actually just one dimensional. Okay, so that's what I'm saying. So again, as you notice, indifference is a big issue, right? So the theory with indifference is ill-behaved because you can always set everything indifferent to everything. And then the theory really makes no prediction. So I need to rule it out. So what I'm telling you really here is that indifference, if it happens, it actually never has any chance of happening, right? Because as you see, we're putting here that any perturbation around a point breaks indifference, right? So what we're doing effectively is we have indifference because it's technically nice to have it. It's easier to derive our theorems, less of a mouthful, so clearer to do mathematically, more elegant. But at the same time, we don't want to do much with indifference, right? So indifference is really not theorizing properly, because the moment you have something different to each other, anything can happen among those choosable sets. So in terms of predictions and of scientific prediction, indifference are an issue, right? So we want to avoid them and limit them. So local non-association, the main thing it's doing is limiting the scope and importance of indifference, right? So everyone understand that? Okay. So now for our purposes, also that gives us something nice, which also we visit in the summer, and is that we're just gonna live in the budget line. So for this particular problem, we always want to be at the boundary, right? So we're not gonna be interested in things that are below the budget line. We're always gonna be spending everything possible. And then the other properties we also studied in the summer is that the Marshallian demand, XPW, has the following properties. Homogeneous of degree 0. I can take any scale of prices and income, and then the consumption is going to be the same. And also, we have Walras law because of local association. And then the final two are consequences of additional assumptions. So one thing I don't like about Mas-Colell is that sometimes it introduces assumptions in the propositions, right? It should be done before, but I'm a little bit following Mas-Colell format, but you have to be careful. So here, it actually introduces more assumptions. So on top of being a utility maximizer and locally non-satiated, you're actually, and this part actually doesn't depend on locally non-satiated, it actually depends only on convexity. So if you are convex, and therefore your utility function is quasi-concave, then the set of solutions is a convex set, okay? So take any two elements in the set of solutions. If I take a convex combination, so alpha of the first solution plus 1 minus alpha of the second solution, the combination for any alpha between 0 and 1 is still in the set of solutions, right? That's convexity. And if you happen to be strictly convex and therefore strictly quasi-concave, then you have a demand function that is actually, you have actually a demand function. So instead of having a demand correspondence, you have a singleton. So there is only one point that maximizes it, okay? So the proof is super simple, right? So you can do it yourselves, but you can use a strict convexity, right? So now, remember that if imagine it's strictly concave, strictly convex, and you don't have unique solutions. So any 2 points in the set of solutions will also have to be a maximum, right? So that is impossible because that will be above the other, which means the other 2 are not maximum. So it cannot be. It has to be only one. Yeah. So uniqueness comes through to that, and doesn't really depend on Lockean association. Okay. Now. Okay. So now the key point here is that we have this model, and we have provided some technical properties. The convexity is important because.
Sorry, can I interrupt for a second? Sorry. In the explanation of convexity uniqueness, I'm still a little bit confused how the relationship itself could be convex rather than function. If the less than more than equal to is convex, and so it's
so let's do it graphically, right? So okay. Can you see my
yeah, I can see it.
Okay. Mm-hmm. So imagine I have something non-convex, right?
Right. Mm-hmm.
So I'm trying to maximize this, right? So mm-hmm. I of course have an example of non-convexity causing non-uniqueness, right?
Right.
So now I'm going to have now an example of weak convexity, right? So for instance, this particular solution here is going to be all this segment, right?
Right?
So this is convexity that gives me a convex set of solutions, but is of course non-unique, right?
Mm-hmm.
And then finally, the obvious one, which is strict convexity, right?
Mm-hmm. Then you have a set unique solution.
Yeah. And of course, take any 2 points here, right? And any combination is going to be strictly above, right? So it's not going to be affordable.
Right.
But it's going to be better. Okay. So yeah. So that's basically it. So the convexity are sufficient conditions for uniqueness. They are not necessary, right? You may have uniqueness without it, but definitely we want to assume it whenever possible. And one of the key results of this class is that, at least for finite data, we can assume convexity without loss of generality, which is very interesting. Okay. But before going there, I need this following result. I need you to remember this, the Karushkin-Tucker conditions, right? So the way all this work we did to represent preferences as utility functions are basically done because we can then play with calculus. So maximizing a rational order on a budget line is hard computationally. Do you understand? So have you thought about how complex it is to solve this problem? So imagine you want to solve the utility maximization problem, right? And you ask actually computationally this question. So how complex is this problem? So who here has some knowledge about computer science? Do we have a computer scientist this year? Sometimes we have. No? Okay, but so basically computer problems can be separated in a very broad sense into polynomial problems, right? And into non-deterministic polynomial problems, right? So polynomial problems are easy to solve, right? These are things that are nice and linear programs, for instance. You can easily solve them and they are not going to grow exponentially as the number of parameters grow. So they are easy to solve. Non-deterministic polynomial problems, NP problems, they are easy to verify. If you have a solution, you can verify it in polynomial time, so easy. But in general, they are hard to find a solution, right? And in particular, there is a conjecture that no computer will ever find a solution to them in finite time. Generically, this is the worst bound, okay? So that means there are problems that are easy to solve within that class, but in the worst case, they are not going to be easy to solve. So it turns out that the consumer maximization problem is actually NP. It's actually in the second class, in the class of hard problems, okay? So if you give it to a computer, sometimes some computers will never end up finishing to compute the maximum if you were solving the original problem, right? But now, of course, all this work we're doing is actually to simplify this problem. So we have added continuity, we have added, we're gonna add now convexity, and on top, we're gonna add differentiability here. So if you do that, now it turns out that maximizing this problem now becomes way easier because it's not gonna be anymore a combinatorial problem. So do you understand originally what it entails to maximize a preference relation? So a preference relation is a ranking, right? So any set that is at the top of the, so in the set of maximizers has to be such that is better than any other element there, right? So basically the way to solve it is you go and check each point, right, in the budget set and then verify in polynomial time, you know, whether it is at the top. And that's polynomial, that's fine. But the issue is that you have to do it for every element. And now how many elements do I have? Infinite ones, right? So now it never finishes, right? My computer never ends up running. So not even a computer. Well, we don't know how our brains works, right? So maybe they don't work like computers and that's why we can do it. Maybe we do it, right? You understand that? But at least if right now I do an artificial intelligent agent, right? Like a trader, and I try to make it maximize a utility function, like the broad problem. Sometimes some computers will never end up maximizing, you see? So everyone understand this point? It's very important, right? So now, because of that complexity, we want to remove a lot of complexity from this problem, simplify it, and now make it something that a computer can do because we're helping it. And so the first thing we're gonna do is we're gonna assume, of course, local association. So that means instead of checking every point in the budget set, we just can check the points in the budget line. So we're going from a set to a line, right? Now, on top of that, that's still not enough. There are still infinite points in the line, right? So we have to do something else. So we're going to assume also differentiability and concavity, quasi-concavity. So with those two things, now I can actually do calculus, which is amazing, right? So my problem is no longer combinatorial, but now is a calculus problem, okay? So I take now the Lagrangian, this thing you learn in calculus 3, right? So utility function plus the budget constraint. And of course, we have here slackness and complementary conditions because we have non-negativity constraints. So again, we are gonna learn this more with Maria, but you also did it in class. But the Cauchy-Tucker conditions are already explained. They add these additional conditions and these inequalities because we may have corner solutions, right? So this was covered again in the summer and with an example. And in the particular case, we have interior solutions, and then everything goes with equality, and you can use the traditional marginal rate of substitution that equates the partial derivatives of the utility with respect to good L and good K equal to the inverse ratio prices, PL over PK. So that's pretty cool. Remember the combinatorial problem I described of checking each point in the line and checking whether it's at the top? Now I don't have to do that, right? I just have to check all the x's that satisfy this nice equation. And sometimes this nice equation is just solving, you know, a simple fixed point problem that converges in finite step, right? So very easy to solve. Okay, got it? So that's the magic of the utility maximization calculus. So we converted something super complex into something easy. Okay. Now, what I want you to remember is the following thing. So remember this inequality here, okay? So in fact, I'm gonna write it slightly different for this class. So these are the first order conditions, right? So the utility have to be that the partial derivative of u is less than or equal than lambda a scalar times prices, okay? I want you to remember that. Why is going to be important? Because turns out that I can use those first order conditions to be able to do testable implications that I can test in experiments, okay? So that's going to be the end of the class, okay? So remember that. And the rest are things that we check in the summer, so I'm going to skip them. The first part is the properties of the indirect utility. I already indicated what it means. The value function, properties of it, you can check it again in the summer. It's a little bit repeated here for self-containment. And the Roy's identity, which meant basically using the envelopes theorem to study how the value function, the welfare you experience at a particular price and income level, changes with the changes in prices and income. right? And we discover that we can write demand as basically the gradient or the vector of derivatives or partial derivatives of the indirect utility with respect to each price, right? And this is the numerator, and the denominator is the scalar income effect, right? And we also illustrated as an example why this may be useful, trying to model by polynomials demand, right? So all of this was done in the summer. And we also introduced the expenditure minimization problem, which was this dual problem, where instead of targeting maximizing utility subject to a budget, here we fix a target utility and try to minimize the expenditures to acquire that particular utility, okay? And we basically, I want you to remind you that we did that because we wanted to derive this Slotski equation, which related the corrected or Slotski compensated substitution effects of a demand with these properties of symmetry and negative semi-definiteness, right? So we created this, what's called the dual theory. And so the expenditure function, basically we provided properties and also the Higksian demand, which is the minimizer. And eventually we show this particular, that this expenditure function is concave, which was important for our Slotski equation. And we use the existence of this Higksian compensated demand, which is the solution or minimization of the expenditure problem, to be able to derive the Slotski equation. So using, again, the envelope theorem and Shepard's lemma, we show that there is this equivalence between the Higksian demand and the Marshallian demand whenever I replace income with the expenditure function. And by deriving this, I obtain the Slotski equation, which says that the matrix of substitutions of the Higksian, which is equivalent to the Hessian of the expenditure, is equal to the Slotski matrix. The Slotski matrix, I may remind you, that is the summation of two terms. The first is the substitution prices of the Marshallian demand, which is an L times L matrix, plus another L times L matrix, that is the outer product. So this is the product of basically L times 1 vector, that is the income effects, multiplied by the transpose of demand, which is a vector of 1 times L. So if you multiply L times 1 times 1 times L, right, it's gonna give you L times L matrix, which entries, right, are gonna be these corrected income effects. So together they form what is called the Slotski matrix. And because now this is equal to this element here on the left that came from expenditure minimization, we concluded that the Slotski matrix has two key properties. First, it's symmetric, and second is negative semi-definite, okay? And this was a testable implication of rationality when the utility is differentiable, right? That's a pretty cool condition, but it's still, it's not that useful. So the issue here is the following. I'm gonna summarize first the utility maximization properties through the Slotski matrix, and then we're gonna discuss how useful it is, and then we're gonna try to go to the main result of this class. So if a demand function x, PEW, is generated by maximizing a rational reference functions that are locally non-associated, subject to a linear budget constraint, then XPW satisfies Walras law. Is XPW is homogeneous of degree 0. Moreover, and importantly, the Slotski matrix, when differentiable, is negative semi-definite, and also singular in prices, which is consequence of homogeneity, and finally symmetric. Okay, so any entry that are of diagonal have to be the same. The entry 1, 2 has to be equal to the entry 2, 1, and so on, right? Now, it turns out.
Sorry, quick question.
Sure.
So for this negative semi-definite, so say a good is luxury good, then that wouldn't satisfy the homogeneity of degree 0. That's why it wouldn't be sometimes negative semi-definite. That would be the counter example to that, I guess. Is that correct? Is my understanding?
So define luxury good.
Oh, so sorry. So you want more when the price increases, right? So
okay, so
yeah.
All these are names, right? So that's
names, right,
but,
right.
Yeah, but you define it correctly, right? So you say,
yeah.
I want to define it as something whose own price derivative is increasing, right?
Yeah.
So the demand of the good with respect to its own price, differential change is positive, right? So that's actually, so we know there are two kinds of goods that satisfy that, right? Those are the Giffen or the Veblen, right? So the Veblen goods are kind of what you're saying, luxury goods, right? So things that the rich purchase, right? The more expensive they are, you want them more, right? I don't know if a Veblen good maybe is a diamond, but may seem like a good example, right? Now, the point is this. So imagine now that, now let's think about our model. So the prediction of the utility maximization model with our assumptions is that you have to have a negative semi-definite Zlotowski matrix. So as you well pointed out, an implication of that is that the diagonal of the Zlotowski matrix is negative, right? So, but what is negative? It's negative the summation of the first term here, right? The diagonal here, which is the object you describe, right? So remember that in order for this diagonal element to change signs, given that the first term is always negative by definition, right? Because as prices increase, you can purchase less. So you're going to have always a negative effect here. So the only way it can be overturned is by means of this second term, right? So now the only thing that changes sign here, given that the demand is positive, is the income effect, right? So in other words, you actually need, and remember, this is the key idea of so the negative semi-definiteness requires that the diagonal entries in each of these items have to be less than or equal than 0, right? So that means that given that one term is always negative, sorry, for instance, this term, let's say, is positive, like the Giffen good, then this term here must be negative. So for instance, in the case of, because of the constraint, and that's the Giffen good example in chapter 2 in the summer, the only kind of upward sloping goods that are allowed under rational theory are Giffen goods, because they are inferior goods that they actually are purchased more as income decreases. And that lets you have the own price elasticity positive, while the compensated Zlotowski elasticity be less than or equal than 0, right? So summarizing, there is no way I can have Veblen goods because they will have both positive entries, and that will violate the fact that negative semi-definite requires me to have negative entries in the diagonal. So negative semi-definiteness implies that the diagonal is less than or equal than 0, right? Okay. So in other words, the Veblen goods are not rational. Okay. So those are limits. So for instance, imagine that Tyson said, you know, I found empirical evidence that people buy more diamonds when they are more expensive, right? So you know, this holds for different income levels, and you know, you compute the Zlotowski matrix, and you actually check the corrected Zlotowski compensated price derivative. If Tyson does that and verifies that the slope is positive, then you know you have established empirically the existence of these Veblen goods, and then you say, okay, given that this is not negative semi-definite, then the question is this rational? And the answer is no, right? Because if you're rational, you must be negative semi-definite, right? So that means the implication is that if you find a Zlotowski matrix that is not negative semi-definite, then it must be that the utility generating this demand is not, it's not even the utility. So there is no utility generating this demand, right? As simple as that. So there is no utility generating this. There is no rational model behind it. So people that have this completely unrestricted upward sloping behavior are of course people that are not rational. So be careful with this. You know, this has to do with compensated law of demand versus non-compensated law of demand. Here I'm describing a violation of the compensated law of demand. So it's a very strong violation of the law of demand. Okay, got it? So rationality allows for violations of the uncompensated law of demand, like the Giffen goods, but it doesn't allow general violations like the one Tyson described with the luxury goods. Okay. Yeah, so you're going to the important part, which means given data, can I test utility maximization? So can I actually know whether utility maximization is a good description of behavior? And the way I can do it, of course, is by deriving testable implications. So this is our first attempt. So we have used the duality theory, to derive implication in terms of the Zlotowski matrix, which in principle are objects that you can estimate from data. And because you can estimate demand functions, and using demand functions by deriving them, you can estimate Zlotowski matrices. And if you estimate Zlotowski matrices, you can check the negative semi-definiteness and the symmetry. So have people test that? Yes. So my own work, my first paper is about that, and you can check it if you want. But I actually checked in laboratory setup whether these conditions of the Zlotowski matrix hold. And initially I found that they are not great, so they are not satisfied. But now I'm going to present a more nuanced view of that, and I'm going to do it in a bit. But first, I need more theory. And the first question I want to answer right now, theoretically, is the following. So, okay, so everything is cool. I derived empirical implications of a theory. The question should be now, are the empirical implications of my theory all possible implications of my theory? So are these, in fact, sufficient conditions? So again, this is the idea about warp and garp in the problem set. So remember, I asked you that, for instance, rationality in incomplete data sets imply warp, the weak axiom. But if I check warp in a data set, it doesn't mean immediately that it can be generated by utility maximization, right? So it means that warp is testable implication, so therefore necessary, but it's not sufficient. So it doesn't allow me to conclude for sure that there is a utility maximization, okay? Process going on. So here is the same. So I want to know whether these implications of the Zlotowski matrix are in fact sufficient. So I already told you in the summer, negative semi-definiteness is connected with the weak axiom of revealed preference, right? So that we know from previous chapter, we have discussed it a lot. So this is the warp part. Now the symmetry part is the additional part that adds to the negative semi-definiteness that makes jointly the Zlotowski matrix not only necessary, the Zlotowski matrix with these properties, not only a necessary condition, but also a sufficient condition. And that's basically what we're going to state in the following theorem, which is a very important theorem called the integrability theorem. So in sum, right? So we're interested in what are the sufficient conditions for taking a demand function and being able to get from this the utility function. Do you understand what I want to do? So what will I want to do that? First of all, if you go to the World Bank and you're asked to estimate a demand function, usually estimated elasticity is not going to be the end product. The end product is going to be some sort of welfare analysis, right? So in order to do welfare analysis, you want to recover utility functions, right? You want to know whether people are better off or worse off because of a price change or an income change. So in the end, you want a utility function. So we're going to study now under what conditions can you get a utility function from the demand function, okay? And this is called the integrability problem. So in the first chapter, basically we saw this problem for discrete sets and finite sets, and we saw that we can play with warp and garp to construct utilities. But now what happens in the world of the differential world with infinite data, right? So now we are going to have to do something else. So remember, the Zlotowski matrix is this object, which is the substitution term plus the correction term. Entry by entry, if you don't remember, is the following. Is the partial derivative of entry I of the vector of demand x with respect to price j plus the correction term, which is the change in demand with respect to income of the good I times the quantity demanded of good j. And of course, all entries I, j from 1 to L form an F times L matrix. Now, this famous term by Hurwitz, Usawa, Richter assume basically they tell you that if you have a demand function that for which Walras law holds and the Zlotowski matrix associated with this demand. Remember, this demand may not come from utility maximization. Is actually estimated from data. So you run an econometric model, you estimated the demand, you computed the Zlotowski matrix associated with this demand, and then you obtain it's a Zlotowski matrix and check the properties. And the first thing you check is that it's symmetric. And the second thing you check is that it's negative semi-definite, right? If you do those two things, then you can actually conclude that there exists a continuous utility function that is part differentiable that generates the data. That is, the demand function is such that x is equal to the Rmax for this utility you constructed, subject to the budget constraint. So in particular, the Hurwitz-Osawa theorem is telling you that you can always construct such a utility after checking the Zlotowski matrix, okay? So now what I'm gonna do in the proof is give you a sketch of how this proof works, and then we're gonna do an example. Okay, so again, the proof is a sketch because the full proof is actually beyond the scope of this class. It's an exercise in partial differential equations. So it's beyond the scope of the class in terms of math requirements. But what we're gonna do is the following. So we're gonna formulate a differential equation of the following sort. This is a system of differential equations. So here I have the entry I of the demand system X. And now remember, this has two entries. It has price and it has the income entry. So now price is gonna be the variable. So if you you took ordinary differential equation, think of prices as the time, right? So this is the running variable in this partial system of equations. And remember that the unknown on this partial PDE system is actually a function. So what is the function I'm looking for? I'm looking for what is called the income compensation function. So this is gonna be a function mu of prices, right? That is gonna give you, right, this equality, such that a change in this income compensation with respect to prices is equal to the change in demand, okay? When the income changes according to this function mu of p. So what does this remind you? So if you go back to the expenditure minimization problem, we notice that if you take the expenditure function and you derive it with respect to prices, you obtain the Hicksian demand, okay? This is called the Shepard's lemma, okay? So remember, go back a bit. Shepard's lemma means that take the expenditure function, derive it with respect to prices, and you get a Hicksian, okay? So this is the Shepard's. Now go back to our integrability problem. This looks awfully a lot like a Shepard's lemma, right? So in particular, remember that here you have income, right? But now I'm replacing income by a function. So this function, in fact, is the expenditure function, right? Do you see? So what we're trying to construct is kind of an expenditure function. But right now, remember that this is not an expenditure function yet, because this is just an unknown in a partial differential equation, okay? So this unknown is called mu, and this mu has as a parameters prices, which is a vector. And how many equations do I have here? I have L equations. So these are L partial differential equations, okay? And what is the unknown is a single function, a scalar function mu, that is a function of a vector parameter of size L, okay?
Sorry, so in this proof, we're trying to show the mu is gonna have to end up with the expenditure function. That's the goal of this proof, is it?
And more than that, so we're gonna use it, yeah. Eventually it's gonna become sort of the expenditure function, but I'm gonna use it to build a utility function because the theorem says that I can build a utility function. So I'm gonna
sorry, I kind of lost the goal. Okay. Right.
Yeah. So remember, the theorem of Hurwitz-Osawa is the constructing a utility function. But I start with this object, right? So any partial differential equation needs initial conditions, right? So we have to have some point at which this function is known. Else I just have a family of functions. So I cannot pin down a unique solution. So I need some sort of initial condition. So I'm going to assume, right, that I know this for sure at some point. So in particular, I'm going to know that this is just a normalization. So I can pick any price and income and then fix it, right? So the point here is that this expenditure is going to be equal to the income at this particular chosen price and income pair. I can choose any price and income pair. So imagine income of 1 and price 111, I can do that, right? So this is just a choice at this stage. So now, what does it mean? if there was a solution to this problem, then I will obtain a function that is, of course, a function of prices, but also the initial conditions P naught and W naught. Okay. Now, turns out that symmetry of the Zlotowski matrix guarantees that this PDE has a solution. Okay. So symmetry is used here. So this is called the Frobenius theorem and is pretty much coming from the partial differential equation literature. If I have this Zlotowski matrix and is symmetric, I can ensure that the partial differential equation written here has a solution. Okay? So at this stage, I use symmetry only to guarantee that this problem has a solution. Okay? So therefore, I take the solution to this problem, and this is the solution mu P naught W naught. So pretty much, I use the solution to 1 to define a candidate indirect utility. So a solution exists because of the Frobenius theorem, and also this implies that this function is continuous on the second argument and differential. So it turns out that the second argument is the initial conditions P and W, right? So if now I change the initial conditions to any other P and W, and I do it in a very close epsilon ball, then the solution itself is going to be very close, right? So this is a continuity. And also it turns out this is differentiable on the second argument. So look what I do here. And this step is very important. Now I'm going to define an indirect utility function from this expenditure function by fixing a price in the first entry. Remember, this is a function of the P, and is also a function of the PW. P is the running variable, right? It's like time in the ordinary differential equation analogy. And the second ones are the initial conditions, okay? So this is a function of the two of them, right? Now, BPW is going to be defined by fixing the first argument of this object, mu, to fix a P star. So what we have here, remember, is in fact an expenditure function. So what was the structure of the expenditure function, right? So expenditure function was a function of prices and of U, the utility function, right? And then in duality, what I did is I took the U and I replaced it by the indirect utility, right? Here to obtain the indirect utility here. So this is the duality, right? So who remembers that that part? So I'm just gonna write it in parentheses here. So recall duality said that BPW, right? The income is basically you have the following relation, right? So income is equal to PBW, right? So we know we can get from the expenditure, we can get actually our BPW. So what will happen here is that, for instance, fix a price, I can actually invert it, right? And obtain the BPW from the E. And in fact, I know, right, that BPW, right, is equal to U. So these are the relations from the duality, and this is more or less what is going on in the background. So the key here is that I take this mu function, and I'm gonna fix the first entry to some number. So P star now becomes a physical number that I pick. This choice is I don't care. I'm gonna do it for convenience. You're gonna see in the example. And I'm gonna let it be variable on the initial conditions, okay? So doing that, I'm gonna get an indirect utility candidate. So this is a BPW, okay? So I'm just describing steps. This is an algorithm. So then we're gonna do an example, or you're gonna see this in action. But right now, I'll try to just see the steps so you can connect later with example. So now, I'm gonna use the second property, the first property, sorry, negative semi-definiteness, to be able to actually show that this indirect utility, in fact, is related to a utility function, and actually maximizing this will generate the demand function. That is my primitive here. So the way I'm going to do it basically is I'm gonna invert the demand function to obtain PW as a function of quantities, right? So what is the inverse demand? It means that I can now map quantities from knowing prices and income pairs, okay? So I can go, you give me a price and an income, I'm gonna give you a quantity.
Victor, can we invert any demand function, or there has to be some condition to be satisfied?
There has to be conditions for doing that. So we're assuming here, in particular, one sufficient condition for invertibility here is a strict convexity. Turns out that a strict convexity and differentiability are enough for invertibility in general, right? So, and also actually are also necessary. So you need these two things to invert them, okay? So invertibility comes really for convexity of the utility. So now with this in hand, we do the following, right? So we take this dPW and now we invert demand and now we obtain U of X, okay? And then finally using negative semi-definiteness, and this is the part of the proof we're not gonna do, that's the hard part, we show that in fact maximizing this utility function I constructed is in fact utility maximizing. So let's do an application, and this is gonna hopefully fix ideas. I know it's a little bit hard, but doing the example usually helps a lot. So let's start with two goods and say you estimate a demand function that gives you demand for good one is equal to alpha W divided by P1. I'm assuming that Walras law holds. So that means that the second good is, of course, 1 minus alpha divided by P2, right? So the only information I have to give you is the information of good one, okay? Great. Now, the second thing I want you to notice is that because of Walras law, the second dimension or the last dimension of this demand system is irrelevant. So we are, in general, we don't need to use it. So in particular, you can always just deal with a lower dimensional demand system, removing the final entry. So in the case of two goods, I just need to deal with one good, okay? So my partial differential equation problem is gonna be now just an ordinary differential equation problem, right? And that's what I can do it as an example. We're gonna also do some normalization of prices to simplify. One important key aspect here is that you can normalize this to any level, but you have to normalize this after you have obtained the elasticities, right? So this is gonna come clear in a second, but we're gonna fix the price of 2 to 1 for simplicity. And I can do this because of homogeneity of degree 0. So now you have now x2 is just 1 minus alpha times w because price of 2 is equal to 1. Now,
so Victor, if there were n goods, you fix Pn equal to 1?
So if you have 10 goods, you can fix the 10 good to that. But in general, right, you can fix any of the goods. It doesn't matter which one. So normalizations with homogeneity of degree 0 are not restricted to one good. You can also, for instance, require that the summation of all prices is equal to 1, or that the norm of price is equal to 1. So there are many normalizations possible. The point is that the only thing that matters in utility maximization is the ratio of prices, right? So the ratio of prices doesn't change. If I change price 2 to 1, the ratio of price is the same, right? So only the ratio matters. Okay, good. So what is my differential equation? So is mu prime of P1, right? And then remember that it's of the second price. So the second price is P2, which is equal to 1 here, okay? And now what is the demand? So the demand of good 1 is alpha times W divided by P1, okay? But what is W here? So W is replaced by mu of P1, 1, right? So that means I have here X1, which is basically the function of prices, P1, 1, mu P1, 1. Good. So now, of course, the 1 there, notationally is better to remove it, right? So I'm gonna write again everything in terms, removing the 1 that is always fixed. So mu prime P1, alpha mu of P1 divided by P1 is equal to X1 P1, mu P1, okay? So focus on this part. So this is now is just an ordinary differential equation because there is no longer a system. I only have two goods. I use homogeneity of degree 0 to get rid of the last equation. I only get one equation. I have one unknown, which is the function mu, okay? So this differential equation relates the derivative with the function, right? And through the Cobb-Douglas lemma. Now, I verify, of course, before this, that the Cobb-Douglas has a Zlowski matrix that is symmetric and negative semi-definite, right? So I already did it, and now solve this ordinary differential equation. So this is one of the simplest one, right? Ordinary differential equation. And I just rearrange terms. I assume it's non-negative. And it turns out that I can divide mu prime by mu. And now I have this typical argument that this is basically the chain rule of a logarithm of mu. So this integrating back is logarithm of mu is equal to alpha logarithm of p1, natural logarithm plus a constant. So this part here is just ordinary differential equation, right? Everyone agrees? Okay. So this, is very simple argument, ordinary differential equation. We're not going to do much of that. So if you remember this kind of argument here is going to be enough. And then the issue is really pinning down the constant, right? Because the constant is the one that gives me a family of solutions. So I right now have to fix the constant according to initial condition, okay? So I'm not done yet because I got the logarithm of mu. So I need now the mu. So I take exponentiation, both sides of the equation, and then I get mu, and then of course, I get a k, which is exponential c, and then p1 to the alpha. So this is mu, okay? Now, with this mu solution, I have to now make a change in terms of the initial conditions. So take some initial conditions, price 1 naught, W naught. In particular, these, for instance, we're going to fix it. These are going to be variable now. So they are generic values. And so I just going to solve it. So this is an equation now. So at this initial condition, I know that mu of P naught is equal to W naught. Remember? So this is the condition I set here in the first step. Mu P naught is equal to W naught. Do you remember? So with this initial condition, I'm going to conclude that income naught is equal to K P1 naught to the alpha. And solving for K, this gives me W naught divided by P1 naught to the alpha. Okay? Now I plug in back to the mu function, and I now obtain this object here, which is a function of prices and a function of initial conditions. So the K now became W naught divided by P1 naught, and then P1 star, okay? Here is the key. So in a step number 2, I said that now we're gonna fix prices to a value, a numerical value, the P star. So here in my example, I'm gonna fix the P star to 1, okay? So P1 star is equal to 1. Why 1? Why not 2? Why not 3? Because 1 is nice. You can choose any, right? I don't care about the value. You can pick any value. In particular, I'm choosing 1. So by choosing 1 now, I replace it here. 1 to the alpha is 1. So now I have W naught divided by P1 naught to the alpha. Now I get rid of the naughts because now I'm letting it be variable. So now P1 and W are changing potentially, right? So these two things now become variables. So I remove the naught superindex, and now I have that mu function for P star is equal to W divided by P1 alpha. Got it? And here is the final part, right? So this object here is the indirect utility function, okay? So I need to use it to get back to the u of x, the utility function. So this object here is the indirect utility. I need to use it to get to the u of x. So the final step said invert utility, right? So I'm gonna invert the utility. So remember the system was x1 is equal to alpha w divided by p1, x2 is 1 minus alpha w. So do the following. Take the ratios, x1 over x2 is alpha 1 minus alpha 1 over p1. If I solve for p1, I get p1 is equal to alpha 1 minus alpha x2 over x1. So this maps, as I said, from prices and income to quantities. So, okay. So I get P1 is equal to alpha x2 x1, W is equal to x2 1 minus alpha. Inverse the map. So I can go back and forth, right? So now plug it back on the indirect utility function. So this is the indirect utility function, W divided by P1 alpha. So W is equal to x2 1 minus alpha, and P1 is alpha 1 minus alpha x2 over x1. So replace it back, entry by entry. I do all the algebraic computations, as you can see, and then solve back. If I solve back, what do I get? I get x1 to the alpha, x2 to the 1 minus alpha, c hat. And c hat is just some constants. 1 minus alpha to the alpha, alpha to the alpha. Alpha are between 0 and 1, so they are positive things. So what does this look like? This is a Cobb-Douglas, right? Okay. So now you constructed yourself a Cobb-Douglas. Important things. So does it matter the value of c hat? Not really, right? It can be whatever. And so basically the choice of the P star gives you different constants. Now remember that the utility function is, the same irrespective of any monotone transformation, right? So any of these choices of the numerical choice you make here is just gonna keep the same utility. It's just gonna change the scale. Got it? Okay, so this is the integrability problem. Now, in reality, how you're gonna use it? So in particular, right, for problem sets, for exams, sometimes you may have to do it. And when you're gonna do it, I'm gonna do a simple exercise of two goods. Therefore, you're gonna do just an ordinary differential equation. It's gonna be very rare that I'm not gonna test you in partial differential equations to summarize, okay? But so what do you do in real life if you have to face this? So in real life, sometimes you want to compute the utility function from a large demand system. So in those cases, you have to use numerical methods, right? Or it's even easier than that. Sometimes you already use a demand system that is already coming from a polynomial derived from the indirect utility function. So therefore, knowledge of the estimates of each of these parameters that are already structurally connected to the indirect utility function, you can just reconstruct back the indirect utility function because you already estimated under the constraints of that. So that means integrability is not really necessary because you're already modeling this as coming from utility maximization. And this problem here, is sometimes is done in practice because people want to do welfare, but usually simplified by many practical assumptions one makes. But in particular, the main result here is telling you that checking that the Zlotowski matrix is symmetric and negative semi-definiteness is enough to guarantee under differentiability that you can always build back a utility function. Therefore, the Zlotowski matrix conditions of symmetry and negative semi-definiteness are necessary and sufficient conditions. So in fact, there is no more empirical content than these two things. Okay? So, but we studied in the previous chapter GARP. Remember GARP? Generalized axiom of revealed preference. So what is the relation between this symmetry thing and the negative semi-definiteness and GARP, right? That should be a natural question, right? So we know that warp implies that the law of demand, compensated law of demand holds, and therefore it means that the negative semi-definiteness of the Zlotowski matrix holds. Turns out that GARP implies that the Zlotowski matrix is symmetric. Got it? But GARP is more general, right? But we haven't still shown the relation with GARP. So that's what we're gonna do now, and this is gonna be the conclusion of the chapter.
So for what we did, I just want to understand it. So say we have a data of we have data, price, and wealth, and quantity. And then we say we run a regression and we get the demand function, and that's the data we see, and then we confirm that it satisfies warp and garp, and then from using the fact we can derive this kind of utility function from those data.
Yes.
Okay.
Just one key
That's
thing,
the
right? That's the rough idea. So one caveat is here we didn't give you anything about noise, right? So instead of doing a regression, you will do an interpolation.
okay.
But imagine there is noise and then you can adjust it, right? So people have done it. In general, yes. So after obtaining the demand function, right, you can do all of this. Now, of course, there's an issue, right? Because in real life, you don't get functions. You just get points.
Right.
So
you have to come up with your own model function to. So.
Well, that's the next section, right? So there is a better way, right? So it turns out that you can actually just check the GARP. Okay. So that's surprisingly that people didn't know this, right? But Mascolel or other people, they work on these conditions, including Samuelson, and they were focusing on the calculus world. Okay. But it turns out that there is a simpler world, and this is the world of generalized axiom reveal preference. So I'm going to go over that. So up to this point, this chapter, we have very little concern about the data set that we have at hand, right? We're assuming we have a demand function. As Tyson said, that's not easy fit, right? Because imagine, for instance, you run an experiment, you only have 2 budgets and 2 choices. So then how many demands can they go through these 2 points? Infinite ones, right? And then for each of these demands, you have to actually compute this loss metric. So it's not really practical to do that, right? It's too much work. So there has to be a better way. And then we're going to just deal directly with the prices and consumption. So we're assuming Walras law. So I'm describing completely an experiment by telling you that Pk xk from k equal to 1 to k describes a collection of trials. In each trial, the consumer faces a budget Pk, a price, a slope. And then what is the income is Pk times xk. So the multiplication of both gives you equal the income, right? So I don't need to tell you the income because it's implied. So I give you a budget and I give you the choice out of that budget. And how many of them do I give you? I give you capital K. Capital K has to be greater than or equal than 1, okay? That's in fact, it has to be greater than or equal than 2 because for 1, there is no testable implication, right? So everything is rational. Now, we are gonna redefine the reveal preference relations, but for the consumer world. So remember, these are going to be specializations of the reveal preference relation under local non-association and under the assumptions we made. In particular, local non-association. So we say xt is directly reveal preferred to x, xt r super dx, even only if the inner product of the vector pt xt is greater than or equal than the inner product pt times x. So what is the relation with the reveal preference that we studied in the previous chapter? Well, it's very simple, right? So what is the multiplication of PTXT? Because of Walras law, this is the income, right? Okay, so this is telling me by local association, choices has to be on the budget line. So this has to be equal to the income. Now I have income, and this doesn't have to, there may not be utilities, right? But the fact is that we're assuming Walras law. So Walras law is there, and then something else is below the budget line. So this means that XT is peak chosen at these prices, this budget, whenever X is affordable or is available in the same budget line, budget set, okay? So that's exactly the same definition as before, because we're saying XT is chosen when X is available to you. So now we declare XT directly reveal preferred to X. Got it? Got it? Okay. So now we define an indirect notion of reveal preference, right? And this you know. So imagine I have XT indirectly reveal preferred to X. I remove the super D, XT, Rx, even only if there is a chain of commodities, X1, XT is reveal preferred directly to X1, X1 to X2, and so on until Xn is directly reveal preferred to X, okay? Is indirectly reveal preferred. And so again, this is the transitive closure of the direct reveal preference relation. And so in particular, right, so we're allowing now for correspondences, and in particular, we're assuming basically that these objects live in the budget line and so on. The chosen objects, the other objects may be wherever. So whenever you see a super T, that's an observed object, which is a choice, right? This is a chosen object. Chosen objects have to be in the budget line. And then I'm gonna give you something that is called the Afriad's term. So I'm gonna redefine work. By now, this condition is gonna be only weak cycles. That is also in the order theory part. So a data set pkxk from 1 to k1 here, not 0, is said to satisfy guard even only if the relation R, or the transitive closure of the direct reference relation, satisfies only weak cycles. Okay. So in particular, this is actually the same written with RD or R, but for simplicity, let's write everything in terms of RD. So say I have a chain of revelations. X1 is revealed directly preferred to X2, X2 to ... Xn, and then I obtain that, and then I observe that Xn is also revealed preferred to X1. Okay, so that means there is a cycle, right? But if so, it has to be that the cycle is only in different cycles. So that means that the symmetric part of R. So it has to be that the chain also goes in the other direction. Okay. So in particular, I'm gonna tell you what it means. So another way to write this is that if X T is revealed preferring directly to XS, then it cannot be that XS is strictly revealed prefer to XT. Namely, basically that PS transpose XS is greater than or equal to PS transpose XT with a strict. It cannot be that this holds, right?
Victor, does this hold for warp as well, this definition?
This is GARP. So GARP for this environment is we're using now prices to define GARP for our environment. It's the same definition, but specialized for linear budgets, okay?
Professor, we wrote something twice.
Sorry? Can you say that again?
Because it cannot be X. The sentence, the parentheses.
XS, yeah, X to the power S twice.
Okay, so where did I wrote that? Yeah, thanks. T. Okay, so yeah, so what I'm saying here is that if you reveal something indirectly to another object, then it cannot be flipped strictly, right? You can only have an indifference relation. Okay, so the Afriad theorem tells me the following result, which is a very powerful result and better than the previous one because it can be tested in finite data. It can be applied in any situation. So give me a finite data set of points, right? So I just have budgets and I have choices, prices and choices. There can be a finite number of them. I'm going to tell you, you don't need to estimate the demand. You don't need to interpolate demand. You don't need to compute the Zlotsky matrix. You just need to check GARP, okay? So I'm going to tell you the following, pretty much statements are going to be equivalent. So the first statement is there exists a locally non-associated utility function U that rationalizes the data in the sense that for all k, all observations in the experiment, uk is greater than or equal than u of x for all x such that they are in the budget. So pkxt is greater than or equal than pkx. Got it? So this is equivalent to the data set satisfying GARP. Okay? So that's important, right? So you take the data, you check this condition, which is something you can check very easily as a linear program in a computer. And then this is enough to tell you not only, you can for sure now build a utility function, right? So this subsums any description of the Zlotsky matrix. because Slotsky metrics may not even exist when you're not differentiable, right? You don't even have the demand function here. You only have here points. You see the powerful of the power of this term. You only need finite points. This is an experiment. You only need that. Okay. So you check the GARP on the finite data, and this is enough to ensure that you have a utility function. And if you have a utility function that is maximized, your data will satisfy GARP. Okay. But there is more to it, right? So this is also equivalent to a linear program. So you have a set of inequalities where there are unknowns are scalars mu t and lambda t, which are just constants, indexed by the number of observations in the pretty much in the data set, such that these observations go from 1 to k. And this is such that these inequalities hold ut less than equal than u of s plus lambda s ps xt minus xs. Okay, so these inequalities actually come from first order conditions, okay? So you will combine concavity with the first order conditions to obtain these things. And the important thing is you can also check just this system of equations, which is a linear system of equations. It's a finite number of equations. You can check in a computer. You can put it in MATLAB, in Julia. And if you check this, then you can for sure get a utility function, okay? So you don't need to integrate or solve a partial differential equation. This is the power of it. You just do a linear program. It's very computationally efficient. And finally, and more important, this is equivalent as well to there exists a continuous, concave, and strictly monotonic utility function that rationalizes the data in the sense that is the maximum, right? What is the new thing here? Concavity and strict monotonic. So what is the punchline of the after term? It tells me that in finite data, you can assume concavity, not even quasi-concavity, a strong concavity, right? Concavity, and strict monotonicity. And this is gonna be the same, empirically equivalent to maximizing possibly discontinuous, possibly non-convex, possibly non-monotonic, however, locally non-satiated utility function. Do you understand what is going on here? So Alfred's theorem tells me that in finite data, if you have a finite set of points that you can generate by maximizing a utility function that is locally non-satiated, you can also build a concave utility function that is strictly monotonic that also generates the same data. Got it? So for finite data, concavity becomes non-testable. So you can assume concavity always, okay? So this is a very powerful result, right? So concavity cannot be tested. Okay, so what does it mean? Well, it tells you that that's pretty cool actually, because if you use rationality now, you're gonna get always convex predictions, and you know, irrespective of whatever model you use. And so that's actually very powerful, because convexity computationally is good to check. So if you can check a generated set of predictions, you can actually easily check the boundary instead of checking each point. So short story, it's easier to check computationally. So because I'm running out of time and the proof of the Alfred's theorem is long, so I just want you to, I'm just gonna tell you the following, right? As a motivation for next class. Is that using these results, we can actually go to an experimental data set and then check whether rationality is a good model or not, okay? So I don't have to estimate a demand, I don't have to compute the Slotsky metrics. I can just go and check GARP, got it? From data. So I'm gonna introduce the experiment. So remember, I'm gonna do the proof next class, but for today, the proof is kind of long, so I'm gonna do it later. And then a specialization for strict maximization. Right now, I'm just gonna give you a snapshot of using GARP to test rationality, okay? So there's a paper by Choi, Fisman, Gale, Karif in the American Economics Review 2017, which is one of the best journals in the profession, right? It's famously called top 5 journals. AER, Econometrica, Journal of Political Economy, Review of Economics Studies, right, and the Quarterly Journal of Economics. And this is one of them, AER, American Economics Review. And this is one of the first experiments that have, you know, a lot of observations to be able to check whether rationality is a good description of behavior. And so what these experimenters do? They gathered 93 undergraduate subjects from UC Berkeley, basically. And each of them are given 50 decisions of choosing portfolio choices. So they're given an amount of tokens, which is laboratory money, right? Imagine you're giving 100 tokens, right? And then you're asked to allocate these tokens, budget allocation problem, according to a price vector. This price vector gives you the trade-offs between two states of the world. And these states of the world basically are binary of shiny, right? So these are abstract states of the world, and then each of them pay an amount of money. So if they happen, you flip a coin, and if they happen shiny tomorrow, I'm gonna pay you according to that. So of course, this is an incentivized experiment, so they're gonna be paid according to the outcomes of this coin. And so therefore, this is an economically meaningful problem. So consumers, in fact, are going to be incentivized to choose properly, because if they choose properly, they're going to get more money, okay? And in the end, they actually did it very onerously. So they paid such that this was like 3 times, 4 times what an undergrad did at the time as a payment, as a graduate assistant. Sorry, this is an undergraduate assistant, so on. So they actually earn handsomely. But the idea basically is you are choosing portfolios. You have 2 states of the world. The experimenter controls which state of the world happens after the experiment is done. So they flip a coin, and then they pay according to that. And you do that 50 times. How do you incentivize people to not choose dynamically from this? Is that from the 50 choices, you pick one of the trials at random, and you pay according to that, okay? And this is called payment at random. Yeah, so there are other details that I'm gonna give you later, but this is the broad story. If you want more details about the experiment, this is in the paper, you can check it out. But what you're gonna see, this is the data set. You can see my screen. So subjects are actually presented with this graphical representation of the budget line, okay? And then each of these lines is a budget line that they face. How many of them? You have 50, right? So in particular, this is one of the subjects, and this is the code, 216. It's not the number, we know there's only 93 subjects, but this is subject 216, right? This is the code of the subject. You have 50 lines, and the black dots is the choices that this guy made. So he can only choose 1 point, so it's a choice function. Okay, so what do you think? Is that rational or not? Who knows, right? But I can check GARP, right? So basically, I have prices, I have consumption, I apply my definition, and this is a very easy thing to check. You put it in a computer, in a second, you basically get whether this is rational or not per individual. What I want you to realize here is that here we have individual data sets, right? Per individual, we have 50 observations. Got it? So remember, you know, in the 60s, you know, Cosnes invented national accounting. And then we have time series for countries that were 30 observations, right? 20 observations. And people thought, oh, that's a lot of data. We can do regressions with that, right? So right now, I mean, that's nothing, right? So now we have per individual 50 observations, right? So we can do actually individualized analysis, yeah?
You can choose only 1 point on the budget line, like in the graph, right?
So 1 point is the XT, and the line, the slope is the PT. So in order to check GARP, you have to actually check the fact that the reveal preference relation, you have to elicit them, and then check that they don't form cycles, okay? So let me quickly show you in my board. And then, so for instance, imagine that I only have two experiments, right? And then this is my choice, and this is my choice. So this is an experiment with 2 trials, okay? So what I'm doing in my computer is saying, okay, look, this is X1, and this is X2, okay? And of course, this is P2, and this is P1. So I'm gonna just claim the following, and then you can check, of course. I'm gonna tell you that X1 is directly will prefer to x2. In fact, it's strictly so, right? And x2 is strictly will prefer to x1. So in fact, you have basically a violation of guard. So x1 is will prefer to x2, and x2 is strictly will prefer. Sorry. P I use for strictly to x1. So so what I'm saying is, I did this by hand because there's only 2, but I can do it in a computer for 50 observations, right? And basically, in this case, I found a violation. So I stop my program and I say, I found a violation. This subject is not rational, okay? Got it? That's what I'm doing. This is checking warp. That is a special case of guard, right? So of course, when you have 3 or more, I have to do guard. So I have the 50 and I have 93. Now, turns out, right, I pull them together. The total is going to be 17%, okay? So in total, 18 of the 93 are passing guard. So only 17%, less than 1/5 of individuals are described by the generalized axiom of revealed preference. So what can you conclude according to the Afrel's theorem from this data? So let's go back to the Afrel's theorem. The Afrel's theorem tells me an equivalence, right? So it says this is equivalent, 1 and 2. So what happens if the data set, sorry, this is the version with the strong axiom, which is the unique maximizing. What happens if guard fails, right? The contrapositive. Then there is no utility that can generate the function, right? It's very, very conclusive. So this is the cool thing about this. There is no noise, so therefore we can make really strong assertions. If guard fails, for sure, there is no utility function that can generate this thing. There is no utility at all that is locally non-satiated, right? So it's basically all utility is possible, right? So no way this is rationality. So you see how this is a huge jump in terms of technology, right? For instance, Tyson realized that in order to test this with the Zlotowski matrix, it was kind of hard because I had to go and estimate a demand function. If I estimate a demand function, usually it's hard, right? How do I do it? Most people did a parametric approximation, right? So you did kind of a polynomial world, almost ideal demand system, Cobb-Douglas. I estimate the parameters of that, and then this is just a parametric approximation. So if I reject symmetry of negative semi-definiteness on the parametric demand, then you can always be as smart as and say, look, you rejected rationality just because you're using the approximation of a particular parameter family. But what about more flexible ones? Maybe you're just rejecting rationality because you are not using the actual demand, right? So this is the issue that, testing theoretical models with parametric models, you never know when you're rejecting rationality, the model, or the parametric family, okay? So any tests from all econometrics are bad tests because they depend on parametric choices, you see? So all of them are not good. So Afriat, tells us, look, wait, you don't need that. Just check the guard, simple combinatorial problem that you can check in polynomial time in a linear program. And then I'm going to tell you exactly whether you are rational or not. And using that thing, I conclude that only 12% out of the 93 undergraduates in UC Berkeley are consistent with guard. So therefore, they cannot be described by a utility maximization process. I have 2 minutes. I'm going to let you do the talking. So what do you think? Are you shocked? Do you don't care? I mean, utility maximization is the heart, is the bread and butter of all that economists do. These are 93 individuals in an undergraduate class. Let's think about external validity, right? So, so what do you think, guys? So who wants to participate voluntarily about your opinions about this, as I'm going to ask? So someone's going to talk anyway. So what do you think this implies in terms of our theory?
I have a comment. Like, I don't know, after, like, at the end of the day, economics is trying to, like, especially in micro and in this field, kind of like represent people's behavior. So like I think based off of this, and especially at the time, like 2007, probably because of some of these findings is that behavioral economics has grown so much within the past decade, just because if you're trying to model like economic choice and behavior, yet some of these models are not being consistent with people's behavior, then like there's probably something wrong with the theory. But that's my opinion.
Okay, so I like what Eduardo is saying, right? That's a very modern way of thinking, right? Because you're actually putting data first, right? And so you're saying, look, data tells me that my theory is not good, so we should go to a new theory. Okay, but I have a news for you in a way, right? So I agree with you. I am sympathetic to that view. I think this is the modern view, right? In the time of Mascolel, rationality was always right because data was always crappy, right? So always say, you know, data is crappy, so we don't know yet. So we kind of, right now, sadly, we're not still in the world where we can pretty much conclude, in my opinion, maybe Arthur's right, so this is stage for us, right? I have a minute. But what I'm saying is, you have to really think of the following. So testing is a theory in physics, right? What is the key idea? So remember the thing of the Galileo experiment. And then, you know, from the Tower of Pisa. And then
So we cannot hear you very well.
Okay, so can you hear me now?
Yeah, it's good.
Okay. So remember the Galileo Galilei, experiment. So you take this Tower of Pisa, you throw a coin and a feather, right? And then, you're trying to test the null hypothesis that both things are going to fall at the same speed, right? And what is the issue with that experiment, right? Is that you need to be in the vacuum, right? So you have to be able to be without frictions, other things that are confounding the force of gravity, right? So this may damage your experiment. So, and then Galileo Galilei, what he did is he did actually averages, right? So, you can think of, in the end, fixes for that. But the key is that, so Eduardo, so do you think this experiment is actually done in the void? Do you think these experimenters reach the vacuum? So what I mean is that, you have undergraduates choosing, incentivized by money, but we can ask ourselves, is this money enough? Are they actually thinking enough? And more important, are they understanding the problem? So in the utility maximization problem, the key is understanding the ratio prices. This task asks that you know the relative price by looking at the slope. So you have to be really good at geometry, right? Analytic geometry. So you actually have to figure out from the drawing the slope of prices.
I was wondering, Victor, like, does the number of treatments have any effect on the value of GARP? Like,
Yeah, so they also, because this is choice under uncertainty, they did symmetric treatment. So the probability of each state of the world is the same in the treatment, and then in the control, and then in the treatment they changed it. They made it asymmetric. So when it's asymmetric, actually less people pass. So having complexity on top, trying to understand uncertainty, will also apparently destroy your rationality. But what I want you to say is this. So if we had a perfect experiment, then my conclusions of the GARP test will be, undeniable, right? To say, you fail GARP, you're done. Throw away this theory, work like physics, we're gonna just go with behavioral economics. Of course, one experiment is not gonna make a change, but I think we have mounting evidence that rationality is maybe not the best for everything. So Eduardo is right in that dimension, and that's why behavioral economics grow. So we just have data, so obviously we're not gonna start failing. So Eduardo is right. At the same time, this particular experiment, we have to be careful, we have to be very critical, because there is no really vacuum, right? So there is a world, but it's not clean, because our testing was going on. And in particular, I have my own work, we got advanced the hypothesis with Nail. What's going on in this particular experiment is that people are having issues with perception of prices, because you have to infer the slope of prices from the graphical device. You end up making mistakes of perception, right? So small mistakes on the citation of the slope of prices, you're going to transport them to big mistakes in rationality. So if we take into account these perception errors, then you're going to end up back to rationality. So this is a paper that we just got published in another one of the top 5 tonight, and this is
We
a
can't
guarantee.
hear you again, Victor.
Sorry?
We can't hear you clearly.
Okay, again?
Yeah, your voice keeps.
I think it's my internet this time. So yeah, let me check again my microphone, and then I'm gonna just finish. Can you hear me now? Okay, sorry about that. So this is the ending. So next class, we're gonna prove the Afia theorem, and also we're gonna do this measurement error. So we're gonna allow for misperception in prices. And basically, doing this exercise, we're gonna find out that it's very difficult to reject a rationality still in this kind of data sets. In fact, we don't reject rationality when taking account measurement error. But the more important theoretical advance is gonna be the proof of the Afia theorem, okay? So thank you. I'm gonna be here for questions. So have an hour more, and so feel free to go, the people that have to go.
I have a question.